Hey everyone, welcome back to The Explainer. Today, we're diving into some incredibly cool physics. We're tackling Chapter 15 of the Class 10 syllabus, sound waves. We're going to break down literally every essential concept, graph, and formula you need to totally master this topic. So whether you're trying to ace your upcoming exam, or you just kind of want to know how the sound of your favorite song actually travels from a speaker to your ears, you are in exactly the right place. Grab your notebooks and let's get into it.
Real quick, here's our game plan for today. We'll start with an intro to oscillations, move on to the different types of waves, check out their characteristics, learn how to calculate wave speed, and finish up with the reflection of sound.
All right, Section 1, Intro to Oscillations.
To really get how sound works, we actually have to start with movement. Think about a kid on a playground swing. When nobody's on it, the swing just hangs there at rest, right in the middle. We call this totally free, resting state the equilibrium position, which is marked here as point O. But when you push that swing, it goes to and fro, reaching its absolute maximum distance at points A and B. That maximum stretch from the middle, well, that's what we call the amplitude, or simply A.
So, how do we put this into words for the exam? You'll definitely want to write this down. Oscillation is a periodic motion in which an object moves to and fro at regular intervals of time about its equilibrium position. And the cool thing is, this doesn't just apply to swings. It's the exact same physics describing the pendulum of an old grandfather clock or even a hacksaw blade vibrating back and forth if you were to pluck it.
Moving right along, Section 2, Types of Waves. Let's picture stretching a giant metal slinky out on a table to understand our very first type, which is the longitudinal wave. If you compress a bunch of coils at one end and let go, those coils actually move parallel to the direction the wave is traveling. As that burst of energy travels down the slinky, it squishes coils together into high-pressure zones, we call those compressions, and then spreads them apart into low-pressure zones called rarefactions. And honestly, this is exactly how a vibrating tuning fork punches sound waves right through the air to hit your eardrum.
But what if we change things up? If we take that same spring, or even just a long string, and whip it up and down, we create a transverse wave. In this case, the particles of the medium are moving perpendicular, like completely at right angles, to the direction the wave is actually moving. So instead of compressions, this up and down motion creates these really distinct peaks that we call crests and deep valleys that we call troughs. It's just like watching ripples travel across the surface of a pond. Okay, let's lock this in because I guarantee this is a classic exam question. You always want to distinguish these two by how their particles move. Remember, longitudinal waves mean parallel motion, creating compressions and rarefactions. And fun fact, sound itself is a longitudinal wave. Transverse waves, on the other hand, mean perpendicular motion, giving us those crests and troughs.
Which brings us to Section 3, Characteristics of Waves.
Now, let's look at a displacement time graph. I know graphs can sometimes look a bit intimidating, but it's really just a map of what we just talked about. The amplitude, that lowercase a, is simply the maximum displacement away from that flat equilibrium line in the middle. Just check out the heights at points A and C. Then we have the period, represented by a capital T. This is just the time it takes on the bottom axis for a particle to finish one complete vibration, starting at 0, going all the way up, all the way down, and right back to 0.
So, let's tweak our view just a bit. If we swap our bottom axis from time to actual physical distance, we can spot a new characteristic, the wavelength. We use the Greek letter lambda for this one. You can easily find the wavelength by just measuring the straight line distance between two neighboring crests, like from point A to point E, or between two neighboring troughs, like from C to G. It's literally the length of one complete wave.
Now, what do you think happens if we really speed up those vibrations? By comparing these two wave graphs, you can actually see a super important rule playing out. The wave on the bottom has a much higher frequency, meaning it packs way more wave cycles into the exact same 12-meter stretch. And look what happens to the wavelength. It shrinks, right? So here's the golden rule. A higher frequency means a shorter wavelength. They have an inverse relationship.
Time for a quick knowledge check, straight out of the textbook exercises. We know frequency is just the number of oscillations per second. So, if a pendulum takes exactly 0.5 seconds to finish one single oscillation, meaning its period is 0.5, what's its frequency? Think about it for a sec. Well, if it takes half a second for one, it would complete 2 full oscillations in a whole second, right? So the frequency is 2 Hertz. And flipping that logic around, if a simple pendulum has a frequency of 1 Hertz, its period has to be exactly 1 second. Make sense?
Awesome. Let's move on to Section 4,
calculating wave speed.
This right here is your absolute go-to formula for the physics exam. You definitely want to commit this to memory. The speed of a wave, which we represent with v, is equal to its frequency, f, multiplied by its wavelength, lambda. Super simple, v equals f times lambda.
Let's actually solve a classic textbook problem together so you're totally prepared. The question is, a sound wave with a frequency of 175 Hz has a wavelength of 2 meters. Calculate the speed of sound. Okay, step 1, let's grab our data. F is 175, step 2, lambda is 2, step 3, we just plug those into our awesome formula and multiply. 175 times 2 gives us a wave speed of 350 meters per second. Boom! Easy, right?
Finally, we're at section 5, reflection of sound.
You know how a rubber ball bounces right off a brick wall? Well, sound waves do the exact same thing. They reflect really well off smooth, hard surfaces. And you can actually prove this yourself. Look at this classic setup. If we stick a ticking clock at the end of one tube, that sound wave travels up, hits the smooth glass pane, and bounces right down the other tube to your ear. But here's the catch. If you swapped that glass out for a soft, fuzzy cloth, the sound would get muffled. Smooth, hard surfaces are absolutely key for a good reflection.
And acoustic engineers use this exact principle in the real world all the time. When they build massive concert halls or auditoriums, they install these huge curved ceilings and place large wooden soundboards right behind the stage. And trust me, those aren't just there to look pretty. They literally capture the sound energy from the performer and reflect it perfectly down to every single seat in the house, making sure nobody misses a note.
All right, as we wrap up this explainer on Chapter 15, I want to leave you with one big, fundamental question. When you hear a sound, is it the actual air particles traveling all the way to your ear, or is it something else? Think back to our slinky. The particles themselves are just vibrating back and forth in place. It's the wave, the energy disturbance itself, that's actually traveling across the room. But wait, if sound absolutely requires a medium of particles to travel through, what do you think happens to a sound wave in the complete empty vacuum of outer space? I'll let you ponder that one. Keep up the great studying, and you are absolutely going to crush this exam.